In this video, we're going to introduce the concept of coordination complexes, something that we find transition metals engage in a lot. Our learning goals are going to include the structure of coordination complexes and the nature of ligands that form coordinate covalent bonds. We'll define these various terms as we go through the video. Coordination complex is basically a complex ion plus a counter ion. The counter ion simply balances the charge so that the overall coordination complex is neutral. Now we're going to spend most of our time talking about the nature of the complex ion. It includes a positive metal ion, which will generally be a transition metal, and this positive metal ion will contain empty valence orbitals. That's important because it needs to have a place where electrons can be deposited. So here is our metal ion, and here are some of the empty orbitals that would be found around it. It may not have as many as 4, but it has some. We'll also define an electron-rich species, which we'll call L, that has non-bonding pairs of electrons. That is to say, L is going to be a nucleophile, and it's going to bond to this metal by donating its electrons to it. So it may look something like this. These L's are something we call ligands. So the definition of a ligand is a nucleophilic species that can donate its electrons into the empty orbitals on a metal. So let's talk about these special bonds that are created between the ligands and the metal. We call these coordinate covalent bonds. You'll also see sometimes they're referred to as dative bonds. I don't typically use that word, but if in case you see it, it means the same thing as coordinate covalent. Non-bonding electrons on the ligand are simply donated into the empty valence orbital on a metal. So it looks something like this. So here we have a metal with an empty orbital sitting out, and there may be other parts of the complex ion attached to the metal. And a ligand will come in with its electron-rich center and a non-bonding pair of electrons that it can donate. It is a nucleophile after all. And it comes, and there's an electrostatic attraction between the empty positive center on the metal and the non-bonding electrons with the negative electron-rich center on the ligand. So when these things come together, the ligand actually donates those pairs of electrons into the empty orbital. So this creates what amounts to a covalent bond, but it's an interesting kind of covalent bond in which the electrons didn't come one from each partner, but they both came from the ligand, and they're both donated into that empty orbital. So this distinguishes it, I guess, from other types of other types of covalent bonds. Now, some common ligands can be either molecules or ions. The one thing they must be is a good nucleophile. So what are some of these types of ligands? I'll give you 3 different types here. First, there are molecular ligands. Water, ammonia, and carbon monoxide are all good ligands. In the case of water and ammonia, I think we could expect this because we've already seen how they can play a role as nucleophiles. Carbon monoxide is a new one, and it's interesting in the sense that the carbon is the one that is the nucleophilic center because it has a negative charge. Carbon isn't normally a nucleophile, but in carbon monoxide it is. We also can have ionic ligands, including hydroxide ion, cyanide ion, sulfide ion, halide ions like chloride ion or fluoride ion. And these, of course, are all good nucleophiles. Once again, with the cyanide ion, we see this interesting juxtaposition where the carbon is the electron-rich center, and it has the extra pair of electrons that can be donated. So it actually attaches to the metal through the carbon side of the cyanide ion. Finally, we could have ionic ligands that have 2 possible binding sites. This is true of the nitrite ion and also of the thiocyanate ion. Let me talk about thiocyanate first. It can connect to a metal either through the sulfur or the nitrogen. Either one of those will work, and so it's very versatile in that way, and those actually form different types of isomers that we might see, and we'll talk about that in the next video. But for the nitrite ion, it can attach to a metal either through the nitrogen, which is a good nucleophile, or through one of its 2 oxygens. Those are also both good nucleophiles. So there's a lot of flexibility there and a lot of variability that we can get. We can also have bidentate ligands. What is a bidentate ligand? Well, these are ligands that can form 2 coordinate covalent bonds simultaneously to a metal. So they have 2 nucleophiles that are separated a little bit enough that both of them can access empty orbitals on the metal. Bidentate, again from Greek roots, that really means 2 teeth. So you can think of these ligands as being teeth that bite into the empty orbital on the metal. Okay, some good examples of this. Ethylenediamine is a wonderful example of a bidentate ligand used in a lot of different compounds. The two nitrogens in ethylenediamine are where the ligand attaches itself to the metal, because both of those nitrogens are good nucleophiles. The oxalate ion is also a good bidentate nucleophile. Now, even though it has 4 oxygens, and any of those oxygens can basically be a ligand that attaches to a metal, because of the geometry of this, only 2 of those can attach to a metal at the same time. So that's why it's a bidentate ligand and not a tetradentate ligand. There also can be polydentate ligands, so some that form more than 2 coordinate covalent bonds to a metal. And I'd say polydentate, again, is from Greek roots that means many teeth. I think the most common of these is ethylenediamine tetraacetate, and we won't use that full name all the time. We'll call it EDTA. Now, it's based on ethylenediamine, which remember was a bidentate ligand, but now what we're going to do is we're going to add some acetate linkages to it. The 2 nitrogens are themselves nucleophiles, and they can both attach to a metal through the nitrogen. When we add the acetates, it adds 4 more possibilities for attaching to a metal through the various oxygen atoms at the end of those acetate pieces that are attached to the nitrogens. So this is a very powerful kind of ligand in that it can attach to the same metal in 6 different places, and because it can sort of surround a metal, it has a special name. We call it a chelating ligand. It basically dominates the coverage of a metal ion and can surround it. Now let's talk about some of the oxidation states of metals that are in these complex ions. Complex ion is a metal ion plus ligands. But the ligands also can be charged. As we've seen, certain negative ions can be good ligands. So the total charge on the complex ion is going to be a combination of the charge on the metal plus the sum of the ligand charges. And remember, the ligand charges, by and large, are either 0 for a neutral ligand or negative for an anionic ligand. So that means when we have the formula label for these complex ions, we're going to list the metal, the ligands, and then we're going to give it a charge. And that charge can either be positive or negative, depending upon whether the ligands have a lot of negative charge. They can actually cause the overall charge of this complex ion to be a negative charge. The oxidation state, that is the formal charge of the metal, can be inferred from the formula. Let's see how that works. So let's suppose we have this ferrohexacyanide ion, and it has a formula of FeCN6 with a charge of 3 minus. So what would be the oxidation state of iron in this case? Well, first of all, we have to acknowledge the fact that the cyanide ions have a negative charge, so the total of 6 of them have a total negative charge of -6. So if they're contributing -6, what charge does iron have to make the total charge -3? Well, we would take -3 minus a -6. That gives us a +3. So the oxidation state of the iron in this case is going to be +3. Well, this has been a quick tour of coordination complexes, but I hope it gives you a feel for how they're constructed and what the various pieces mean and how they interact.